Welcome to this discussion on data complexity and geological modelling. I'm here today with Steve Sullivan and you all to discuss the issues that we face in preparing real-world geological data for modelling. Oftentimes, the overwhelming quantity or complexity necessitates dumbing down our knowledge to a level appropriate for the modelling technology that we're using. But this in itself can hide some of the secrets that our data contains. I would suggest that the upfront decision-making needed for current modelling methods means that our final models contain only the knowledge that we knew about before we ran the model. But with exciting new modelling technologies such as machine learning, we have a chance to process quantities of data that we never could before and have a chance to produce models that really teach us about our geology. As exciting as this is, we need to understand what problems we're trying to solve to really make the most of it. So today's session looks to start a discussion between us all on what issues we face and what we want to solve. There is no presentation prepared, but instead we welcome you to participate in today's discussion on the topic of data complexity, and our aim is to use this knowledge to guide development as we move forward. We've broken down the discussion into 5 areas. As we discuss these, please leave a brief comment in the questions box if you have something that you can add. Currently, you're all on mute, but we will enable your microphone when comments come in. So please briefly introduce yourself and join the conversation. Had times been different, this would have been an ideal topic for a well-lubricated round-the-table conversation rather than a discussion from my home office, which, as you can see, doubles as the workshop. The working conditions we're all facing these days certainly add a level of complexity to our jobs, but that's a discussion for another day. As Maptek enters its 40th year in business, we welcome your input into the future, so take this opportunity to share your thoughts, problems and ideas. This will be a very quick session without your participation, so unless you never struggle with complex data, I would urge you to participate today. So complexity in deposit modelling is accentuated by at least 5 factors: data diversity, structural controls, chemistry, data volumes, and external constraints such as the turnover of staff. Steve, I'll start this discussion by asking you what we mean by data diversity and how this affects the models we make.
Yeah, thanks, Richard, and thanks to all our listeners and viewers, and welcome to your contribution. Yeah, data diversity, I guess, going back when I started as a resource geologist or mine geologist 35 or more years ago, it was quite simple. You know, I had the morning activity was go down the core shed, log the core, so collect geological data. In the afternoon, merge those with some assays, manually draw some cross sections, do some interp, and continue on that on a daily basis. So really, there was only 2 sources of data. It was manual logging by myself and my team, or analytical data. So it was relatively simple. But roll forward, 3.5, 4 decades, and the world has got a lot more complex with technology, and that technology is good in terms of it's able to capture a lot more attributes of the data, of the geology, of the rock mass that we're investigating, understanding, reporting, modelling, and passing on to our engineers to optimise the extraction. Sources such as handheld XRF instruments. We're talking also about core scanning. We're not just photography, but also taking spectral measurements from core. We're talking geotechnical information in terms of RQD, rock mass ratings, Q prime, going to some geophysics. And even on the micro scale, we're starting to see people using LiDAR to get very, very detailed information about their core, their fractures, the composition of the fractures, the roughness, and probably using some spectral analysis. You can also use the infill. So you can start to see there's a diversity of information that can be used in your modelling process. Unfortunately, as I've gone around to many mines and with customers around the world, and I'm sure too, Richard, you have, it's not often that you can see everyone using all that full richness of the data. And I guess this discussion, and certainly love to hear from the people on the call, and looking at the participants, we've got people from all around Australia and overseas. some of your experiences and how you're integrating or how you're taking that diversity and adding to the modelling, making sure that the best possible model from a geological and resource perspective is then getting pushed downstream to our engineers, our geotechs, and the people that add further value to the resource model that we build.
I think that's a good sort of place to kick off some discussion with the people on this call. And I put a question out. What is the most interesting data that you've collected, and perhaps something a little bit left field that you have incorporated into your modeling system, either directly through some numerical means or indirectly as some sort of more qualitative inputs? So if people could put in some comments in the question box, and we'll get the team to tee you up to come on. It might sound a bit like talkback radio, but it's really going to help if we get some input from this early stage.
And I'll trigger off one, Richard, while we wait for some input, is the working on lithogeochemistry, whereby you've got a whole lot of whole rock analysis. You might have trace element and element analysis as well. And using that to come up with through some type of clustering analysis or some type of set of rules to build proxy domains. So, working on a project a couple of weeks ago, we had a complex chemistry there used in a grade control scenario, can also be used in a resource modeling scenario, whereby there was a set of a suite of 6 or 7 different elements, and they were used with a set of rules to build almost 20 different lithogeochemical domains. Now, you can do that through not just sets of rules where, if copper is above 10 and gold is below this, come up with unit A. But you can also use, in this particular case, rules that are spatial as well. So whereby these units, A, B, C, and D, only occur above this type of boundary or unconformity. And units, F through to G, occur within this solid domain. So you can use that combination of numeric and also spatial information to come up with a set of domains. Now, all of this is data preparation that is required prior to you starting machine learning. So the machine learning approach is a very data-driven approach, and it's up to you to ensure that your data is in the correct space before you present it to machine learning. Otherwise, like any system, you put in things that aren't quite right, you'll get a result that's not quite right. So, and that's an interesting process, and we've discussed that in previous sessions about presenting the data, and even if it's not squeaky clean on the way through, the speed of machine learning, the speed of you running domain MCF between 5 minutes and maybe half an hour, maybe an hour for a big deposit, you've got a result. You can then spend time, instead of working on the data, look at the result, and the eye is very quick to pick out problems in the data. We have got a very good way of detecting things that aren't quite right, or as geologists saying, hey, that model doesn't represent the geology that I've got in my head or that what I understand it to be. Go back into the core, into the chips, into the photos, and make some reassessment of some key areas. Have a look at that if you need to, make some changes to the raw data, run the process again. So it's a very iterative approach. You can use it not just as a data validation tool, but ultimately to build a model that best represents your mineralization and your understanding of the mineralization. So your lithogeochemistry and those cluster analysis is one area whereby you're taking things that aren't just pure straight logging, you're using a combination of this data diversity to integrate into a new thing for modeling.
I think one of the topics we'll talk about later is more to people controls in the system and what that has on our modeling. But perhaps we can equate some of that back to our data diversity as well. And traditionally, we think about diverse data being our logging, our XRF, our tools to take very specific measurements of what we're looking for. But are we thinking about what additional data is out there that machine learning or other techniques could be incorporating? I've been at sites where there's been problems with data that's been eventually traced back to particular drill rigs or particular crews doing things differently, pushing the drill rods harder than they should, not recording things as they should. It's something that manually can be tracked down, but in this age of sort of machine learning, there may be a lot more types of data that we can feed into these modeling systems and have machine learning come up with some suggestions about what's going on rather than it only being down to us.
And another attribute, Richard, or another consideration with respect to that data diversity is that the data that's coming in from various sources has a different quality and maybe have a different set of parameters that we need to consider. So you might be getting data that's analytical data from your assay lab that's to the nearest ppm. You might be getting data from the handheld XRF scanner that's plus or minus 100 ppm. You might be getting spectral data, which you can do. It's a proxy for some of your rock types, and that has all got a different level of determination. And that's one of the challenges of how that you dovetail and integrate all that data so that if you're using proxies for geology, how they match to what you have observed. And I guess the calibration between physical known data versus some proxies, it needs to be experimented and proven before just applying across an entire deposit or an entire mining camp.
So with those different data types that Steve sort of mentioned, putting this out to the people on this call, what are these big items or these areas of data that you're currently collecting that aren't being used efficiently or you need to get into a modeling system? Remember that we're trying to take your concerns about data, take your needs and sort of think about the future and how we can incorporate it. So now's a perfect time to sort of put your vote for what data isn't well represented in your modeling system, but it could be in the future with different techniques or processes added.
Yeah, so following on there, Richard, one technique that we've used very successfully in coal with our coal customers over the last 4 or 5 years is taking measurement whilst drilling data from autonomous drill rigs. So we're pulling that data through the Wi-Fi back into the server in the office and incorporating that into the modeling process. Now, the coal geology stratigraphy is generally somewhat competent units, then going through your coal, which is generally fairly low density, fairly easy to drill through, and then going through some harder footwall. So we're pulling off rotation on bit. We're talking about bit speed, penetration rates. All of those we have used successfully as proxies for coal, so that very quickly you can get a build up of your top of coal, your floor of roof and floor of coal, and feed that through to your blasting team so that they can ensure that they get the loading of the holes, the decking in the right place. So that's proven technology in the coal area. We've started to look into taking that measurement whilst drilling as more and more drill rigs pick up this information, pick up the telemetry and the feedback from the drill rigs into the iron ore space and then into the metalliferous space. And that has thrown up a lot of challenges. And those challenges being that something that is hard doesn't necessarily mean it's economic, or something that's not hard doesn't mean it's economic. Things that are weathered versus things that are unweathered, altered rock versus unaltered rock. So when you're dealing with physical parameters such as drill rates, fractured versus unfractured rock, you could have something that's mineralized and of economic importance with any of those characteristics. So the field training and the learning there is a lot more challenging to be able to uniquely describe. But still doesn't mean that you can't use it and then put some level of uncertainty around that data. And there's certainly seen a lot of modeling recently where the reliability of pieces of information, if you physically assay that core, that has a reliability of 1. If you're using a proxy through a PRXRF, maybe that's a priority or reliability of 2. And if you're doing some other techniques, you've got different levels so that you can take that through the resource modeling process and have that reliability when you start reporting on your resource.
So really getting all of those things with their different confidence, measuring the same item different ways, while none of them might be a perfect measure, if we can build that up in a machine learned model where it can make predictions based on large amounts of diverse data about what our rock mass is, we may be able to get some information that we couldn't before with enough reliability from any one of those methods on their own.
That's correct. And another example there, recently working on a project where the geology has been logged in the drill core, very nice, good records. Um, but the geotechnical information has only been logged in about 10% of those drill holes. Now, in an underground scenario, they want to push deeper. They want to build geotechnical domains. And looking at the geotechnical data being only representative 10% of the observed or sampled rock mass, it's very hard to come up with a good answer. You get big fuzzy shapes, which to present to mining engineer, there's too much uncertainty and there's too much risk. So, in this case, we took the geological information, took the lithologies, built a machine learning model with domain MCF, and not just the mineralized section. We took all the data, even the data that was a kilometre away from the deposit, and that looking at the entire portfolio, that entire landscape, showed a lot of regional structures and big structures that then set the framework from which the very sparse geotechnical data could be analysed and helped build up some geotechnical domains. And the secondary to that, we did an alteration model, again from the geological logging, to look at the impact of the alteration and potential impact on geotechnical parameters. So, the combination of, here we are using machine learning to build geology, but we're actually, our outcome is in the geotechnical and geotechnical space. So, don't be afraid to cross disciplines and use data accordingly.
I think that feeds very nicely, Steve, onto the next topic of discussion, being the structural controls, and how well are we modelling these structural controls that might govern our mineralisation, our rock mass, and other sort of factors.
Well, I'll go back to an example when I was working in an open cut, and it was a gold open cut. So I won't say exactly where, but the push was for production. So we would go down there, we would get our grade control samples, and we would just mark out the dig lines, and our focus was to make sure the stuff inside the dig line went to the ore stockpile, and the stuff outside went to the waste. In terms of logging, in terms of face mapping, in terms of structural, we had no time to do anything like that. And having experienced many different production environments around the world, there is a lot of pressure just on digging and getting that, and that's fine. That's an ore control, but there is an incredible value in mapping in the pit, mapping underground, or if you can't physically map, use some of the remote sensing techniques like our eyesight lasers and Point Studio, where you can capture the data within seconds or minutes, and then spend your time in the office, doing the structure and taking the measurements, and then integrating that into your model. So understanding the structure in the pit, but also understanding the structure outside the pit. When we built the machine learning system many years ago, structure was not even of interest. We were building it just to look at lithology, build lithologies, and then once you've built your lithology, do your standard grade estimation constrained within those lithologies. But as it turns out, a lot of the deposits out there, as we all know as geologists, have formed either by structure or have been structurally altered since their emplacement, and often most complexly. And in those scenarios, often, especially complex Archean gold deposits that I've been looking at recently, the intense structure has, and if you're just looking at, say, gold grades and trying to contour gold grades, it gets very hard. And it gets very hard to try and work out if that's geological or I'm just doing a contouring exercise and I'm not really taking into account the underlying geology. Now, having looked at gold, but then taking into account the lithologies that are often mapped, and I looked at a project last year, I think, and we had over 100 different rock types that were logged in those lithologies. They weren't really looking at that. So, we tried to build a contouring or a grade shelled gold model, went back to the lithologies and incorporated them all in all their complexity, and found out that there was a lot of information that could be drawn out of that. Now, the machine learning model in this case only took 20 minutes, and there was quite shallow dipping structures through the deposit, displacing what they thought was some of the last late stage dikes that were going through that. And that structure we could work out through no input from the geologist, just throwing the data into the machine learning system. we could work out the different structures and their, I guess, the generations of structures. And that helped then come up with a new area and new positions to target. So I'm sure, Richard, you've seen in your time some deposits that are quite complex, especially some of that coal in New Zealand, which I had the misfortune to try and model many years ago, but you're working all the time. People think coal is simple until you go to New Zealand, finding that it's running vertically and it's all over the place.
And that's the classic New Zealand geologist problem. You get 2 drill holes only 20 meters away, and anyone else would correlate them with 100% certainty, and you realize you've got 2 or 3 faults in between those holes. And the next mine next to you is vertical, where your mine's horizontal. So understanding that structure is important. And I wonder if we are doing enough to think about structure on a regional geology sense. And we certainly can model what the data gives us. And that's one good source of truth at that sort of mine level or at that grade control level. But when we're making resource models and we've got knowledge of the regional geology and the amount of structure and the confidence that 2 holes will correlate, even though they're close together, how we build in that more regional level of complexity, maybe that's something that we get through an uncertainty parameter that can carry through rather than a physical offset in our model. But is that something that we really need to be pursuing, how to get that large scale knowledge into our fine detail models?
Yeah, and the structure I've seen so far, it's come automatically out of the system. You know, a lot of people are used to imposing structure on a modeling system. In this case, you know, we're just taking your data, and of course, densely spaced data is best, and the structure is actually coming out of that just by a sheer spatial distribution, the correlation of that in space. And you know, I have had several data sets given to me. Just with the say the lithology data, model them up, and while we're having a demonstration, someone will send via email their structure or their shapes and domains, and it's surprising how good the machine learning model has come up with to replicate something that's been very handcrafted and customized and very accurate. And in other cases, we've come up with some surprises too, where no one thought any structure was possible, and machine learning has thrown up a structure, and then people have then gone away and think, well, let's go back and investigate that. Is that a mathematical artifact, or is that reality? And so I guess in that case, it's giving you another set of ideas. Just like Richard, if I give you a data set, you manually build it up, you'll come up with a different interpretation as I will, and all the people on the call, I'm sure, out of I think we showed that in the last webinar, we had one section and we came up with 20 different interpretations. So it wasn't a unique way of interpreting the data. Same with machine learning. We're getting an independent view of that data. Doesn't mean it's right, but it's certainly something worth considering, just as you would share your model with geologists, your fellow geologists, and have a discussion about which is most appropriate.
And I think that concept of having the machine learned model as another geologist in the room is something sort of really powerful, and a geologist who's worked on one particular rock type, one particular geological setting for decades is going to have a very clear view of what they think the geology is like in a similar setting. Moving machine learning forward, perhaps we can feed into it that learning on multiple similar deposits that have the same sort of geology, so that the predictions that we get are based on something that we believe to be similar as well, rather than it only being on the data that we're feeding into that system.
Yeah, and that follows on from the comment that we've had from Colin, who I know is a structural geologist who's on the call, and he's just mentioned that large-scale structures need to be considered more significantly than they really are at the moment. And people are focusing in on their ore body, but not looking at the context and the setting. And I know when we study geology, we look at ore body models and ore body settings, but I guess when we get into a mining scenario, we're tunnel focused like I was when I was doing open cut grade control. Where's the ore, dig it out, get it into the right spot. We're not looking at the bigger picture. And sometimes that bigger picture, understanding that helps us know where to direct our attention, knows where to target the next part of the ore body. And structures are often the thing that will make our ore body disappear. And I know New Zealand, Richard, working with a coal mine many years ago, underground scenario, they come to the end of the shift and there's no coal in the face. Where's it gone? They've hit a fault, they've hit a stone band. You've got to know, well, should we go up? Should we go down? Should we go left, right? And understanding the structure is key.
And I think understanding structure is definitely key, like you say, and we've got more power to understand where it's gone. But even at an early level, knowing that it might disappear, even if we don't know where it's gone, just based on that likelihood of the regional geology, I think there's a lot of power and uncertainty that we're not quite harnessing in our geological models.
So, Richard, we'll move on to the third component, which is the chemistry of the deposits. And again, when you started, Richard, we would assay probably just for the elements of interest. They were an expensive assay, and you just got, in my case, copper, lead, zinc when I was working underground, and that's it. You didn't get everything else. Nowadays, in fact, probably the last couple of decades, you'd end up with some type of ICP scan of 45 different elements, and often that came at the same price as if you did 2 or 3 elements. So a lot of that data is not necessarily being used. And again, that richness of the data can bring out various different factors, whether they be subtle alteration features, whether they be the distribution of deleterious elements that may contribute to your concentrate. And I think the ability to take a whole lot of elements, and if you take 45 elements and then try to look at the cross correlation with them manually, I think you'd never finish. So the ability to large systems, and when we're talking machine learning, we're talking cloud compute, we're talking multi-parallel systems, we're talking about matrices that are 1,000 by 1,000 inverted, and not something you can do manually. And that complex chemistry, I think there's a lot of stories in there that we can, again, bring into our deposit modelling to help, again, just fine-tune the work that we put together.
With that, I think the big assumption that we make in our current modelling is we've got, like you say, we might get those 50 elements for free when we do our scanning, and then we know that we're not going to be able to do variograms between all of those variables and make an LMC and model it using traditional kriging. But we know there's a lot of knowledge in there. We know that there are relationships, and we only model the key ones, the most important relationships, because of a time-based, a computing-based, all of these limitations of our current modeling. But we have systems now that could potentially deal with that data, like you say, which is very exciting. But a lot of that is also relationships that we might have never thought would exist that might come down the track. So rather than it just being chemistry driving mineralization, or perhaps down the track we realize we have some mill constraints, some contamination, some recovery problems, or rock mass problems, or something that there may be a relationship that's hidden in that chemistry. And if we've already lost that from our final model, we need to go back to the start and model everything to start looking into where that problem is. Whereas if we are able to carry more of that information into our final model, really use the knowledge buried in that model as a tool for understanding, a tool for saying, well, what's the relationship between this and this, or how does this vary? Or have the computer smart enough to tell you when something is of interest or concern. I'm not sure if anyone's had any of these surprise chemical relationships come up. Certainly put a comment or feel free to grab the microphone if you want to talk about any of these situations where down the track you realize that something was important that maybe you hadn't been assaying or hadn't been modeling up to that stage.
Yeah, so I got an example from a customer a year or two ago where they did have a range of data and looking at associations between arsenic and lead in geochemistry in exploration, and looking at titanium and a few other elements, and a lot of people had looked at those, and this spreadsheet was 45 columns wide. No one had gone out to Z to look at zirconium. And it turned out that there was a really strong zirconium anomaly that helped track down some of the zones of interest. And because no one had scrolled that far to the right of the spreadsheet to find it, no one had found it. So interesting, but there's still a lot of associations to be found in data that sits in public records, that sits in open file reports, sits in our various different government databases. Another I guess what we're also talking about is now really termed as geometallurgy, where not just the chemical nature of the rock, the raw assays, even with this big suite of elements, but also in things like grindability index and some of the material properties that geomet people analyze for. So that kind of non-additive, but they're also very important. A customer who, if you get a certain chemistry wrong, the material in the process plant turns to a gel. So a gel then clogs up all your pipes and all your process. So getting the chemistry right and getting the classification material right in your model is very important, because you end up closing the mill because it's all gelled up. You end up a lot of downtime and a big problem.
I think your 45 columns example rapidly leads on to the next topic of data volumes and the amount of volumes that we can or we have been collecting in the past and not doing anything with, and now we're getting an order of magnitude. You can head out to the pit with a laser scanner or a drone or some data capture device and get gigabytes of information in seconds, and we can get a full suite of XRF analysis at the click of a button. So data volumes, what are we really dealing with now that we weren't in the past? How is this compounding, and what are we going to do about it?
Yeah, so data volumes, not just how we're looking at data diversity in terms of what we talked about earlier, but each of those different techniques and each of those sensors is producing much, much more data. Some of the latest core scanning spectral measurements, they can end up giving you terabytes of data in just a few minutes. So not only is it the size of the data and the different formats of the data that have to be meshed and integrated together, but it's not the real time, it's the near real time nature of that data. So that data is coming in quicker than ever before. I worked in mineral sands many years ago, mineral sands exploration. I drill 10, 20, 30 holes a day, shallow RC air core holes. I would bag up the samples, send them off to the labs. 3 to 6 months later, I will get the analysis back. Completely useless to me in the field at the time, because I can't make a decision on what to do with the next hole based on my manual observations, which I did at the time. Yes, I've got heavy minerals, keep drilling in this line, go back and drill one previously. But really when I was looking at zircons, which were almost colorless, you couldn't make a call in the field. You had to wait 6 months later, in which time you'd completely forgotten where that hole was on the significance. Now that's an extreme case, in member case. But often turnaround for data when you're using spectral scanners, you can get that data within minutes of getting the core out of the ground. You can do your XRF, handheld XRF within minutes, and so you've got that data that you can use to update the model straight away. So you're not waiting. So you can present, even with these data volumes, a quicker model, a faster model to the engineers. Now, resource model, which currently people are do once every 6 months or 12 months, that cycle doesn't really matter. But in a grade control, in an operating environment, the faster you can turn around the data, the faster you can turn around that model and get it to the diggers on the ground, then the faster you can make those decisions, the faster the engineers can make a call on whether to put that to low grade stockpile, to whether they're going off mill feed, et cetera, et cetera. So you have to have a process that not only deals with the data volumes, deals with the integration of those data, but also the speed, so that you can process that data. And that's where machine learning has that ability to process. We can dial up a massive computer, far more than you could possibly ever run on your desktop or in your mind. We can dial up supercomputers, pay a bit more money, you get a faster computer. So if you want it down to half an hour, we can do that. If you want it down to 10 minutes, it's just dialing up a bigger computer. So that availability of cheap cloud compute allows us never to be working with old data. never to pass on a model to the engineers. So instead of having a resource model done every 12 months, we could have a resource model done every month. We could have a resource model done every week. We could have it done every day. So as data comes in, and I know we're building a grade control system for a customer in Canada at the moment, and they're drilling 70 deep RC holes every week. They're going to have a new grade control model every day or every week. It's only taking an hour and a half to generate. So from drills to final block model. So we're going to get a better quality of information to our engineers to make their decisions.
One of the big powers that you mentioned about machine learning is the ability to do things quickly, and you're only limited by the server that you want to pay for in the cloud. There's no sort of limit at that end. But the flip side of that is with data volumes comes bigger models, and certainly something we're thinking about in the future is how we present these huge data collections to users. So I'll put a question out to the group. How big are your current models, and are the models that you are creating limited by what you can practically use in the current environment? Would you like it to have more detail, either at a block size or a number of variables? Would you like more information in the models? And is that really a limitation of your current systems, our current systems, with dealing with a sort of finite amount of data for an end user? So let us know, how big are your models? Are you dealing with 10 gigabyte models? Is that usable? Would you like 100 gigabyte models? Where is the cloud that we need to be aiming for? Remember, we're trying to help drive the future, everyone's expectations and requirements. So let us know. Or are you happy? Is the end user happy with their 200 megabyte model? That's all the data the end user could use anyway, and then that's not really a driving factor for where we go forward. So put a comment in the questions box. It can just be a comment we can read out. If you've got some examples you'd like to join the talk show, then let us know that as well, and we'll unmute you and hand over the talking from Steve and myself.
Yeah, and Richard, just to throw something in there, the biggest model I've worked with in terms of number of blocks is about 280 million blocks. So that's quite a lot. 30 gigabytes in size, and so that's quite a weighty size. To certainly don't want to be shifting that around your network too often. We have development prototypes where we have that data in the cloud, and instead of running the entire model every time, you just run a part of the model, which is where the data has changed, and that's just a prototype at the moment. But that stuff's coming. So it's instead of building your 3 kilometers by 2 kilometers by 1 kilometer every time, you just do the bit that's changed. It makes sense. And the beauty about machine learning is that it only impacts the part that has got new data. It doesn't impact other areas which have been previously modeled and the data hasn't changed. In terms of variables, we've got a customer with 1,600 variables. So even though their physical size, their spatial size is not large, when you start having that number of variables, and we're talking a lot of domains and a lot of geometallurgical variables, the combination there adds up very quickly. And already we've got a lot of data and people using a lot of data, but the challenge for us as a supplier is to make sure that is usable and you have a good user experience, not sitting there for 10 minutes while things load on the screen. So, and I know we've got new graphics engines and all sorts of coming up, but that's the important. We're looking from you as a customer saying, hey, this feels awkward, and let us know, because our job is to make it not so awkward.
I think that idea of local updates in a bigger model could really change the way we think about geological models. And we certainly have this concept of one global mine, sort of quarterly, monthly, annual sort of model that we keep up to date. But if we want real resolution, we go to very small grade control models that have a much finer detail. But is that because running that whole resolution for the entire mine would give us models that aren't usable? Is there a place in the future where we combine the model from these independent models into a true global geology model of where we're working, which has all of the information that you can extract at the granularity that you want for a given task, but we're really just keeping one geological model with all the knowledge.
And Richard, that leads us to our fifth point, is in terms of some of the, I guess, the non-functional or the non-technical constraints about, working with complexity, and that is having a single model, and also having a single model that is well documented, well audited or auditable, having some automated or semi-automated processes that run that model. As we've seen over the last couple of decades now, that is certainly in Australia, the fly-in, fly-out operation, or in my case, years ago, drive-in, drive-out operation, is becoming almost normal. And with that comes challenges on having consistency in logging, having consistency in modelling approaches, consistency in thought. We've seen, Richard, some great control procedures recently where there were procedures, but there was a lot of room for geologists to have some initiative in the way they modelled. And that's not necessarily a good thing in terms of coming up with a consistent product. And you need a set of rules that are agreed by everyone. That's what we're going to do this week, this month, this year in terms of our products, especially in a multi-product environment where you're producing different products for different end customers. So having that transfer of people, maybe that inconsistency of thought. It also exists in multi-generational mines. Some of the customers out there have got mines that have been going for 30, 50, 100, 120 years. And, you can't escape the fact that there's different logging, there's different thoughts, there's even different names for the same rock over those years. And that's, I guess, standardization and normalization needs to be built into a system, especially when presenting it to a data-driven machine learning engine, because if you call something samopelite and someone else calls it quartzo feldspathic gneiss and someone else calls it sandstone, you're going to get three different rocks instead of a consistent unit. And I've seen that in other models where dikes have been mapped. One hole in the fan of underground drilling says rhyolite, the next one says porphyritic rhyolite, the next one says rhyolite, the next one says porphyritic rhyolite. So you just take that modelling code in and you model it, and you end up with an alternating Barber's pole of dike, which may be right. It may be it's a rhyolite dike with varying chemistry. But also, you could just say, hey, look, it's a rhyolite that has some porphyritic tendencies, call it all the same, and build into a consistent unit. But again, when doing this, I always make a new field in my database. So I always keep the observed data separate, and then I have a new modeling code that I do my experimentations with. So some of those I guess non-technical things there in terms of having different people, having different processes. And also we're seeing more and more operations out there using a lot of different software. So, I've seen in the most extreme case, one of our customers have 8 different pieces of software that their resource geologist needs to learn. So you immediately have a problem in terms of bringing people into the organization, because they suddenly have to be proficient with 8 different interfaces, 8 different ways of working, importing, exporting, transferring data between those processes, and that can all lead to errors creeping in. It's very hard for one piece of software to do everything, but at least rationalize to something that is a little bit simpler, provides less for the IT department to manage. Also, if you set up automated processes, have a software upgrade in one, that might break an automated script or automated process, and then the whole thing falls over. So I guess there is something, we're talking about complexity, but there's also another counter to that, also simplify, and simplify to manage complexity, if that's just
I think simplification is the aim of the game, and it may not. We certainly don't want to simplify the geological model that we're making, but we want to simplify the way that we make the geological model. So what we can do to really make that process easier while also gaining more geological knowledge, I think, is what we're all striving for, and machine learning's done that. Has been a huge change in that you can throw data at it and it will interpret structure, it will interpret grade, it will interpret confidence, it will interpret all of these things that you may not be specifically or directly asking for, but by the nature of the way it works and the decisions it makes, it can do that. One of the nice things that I think you brought up, Steve, was fixing your logging. We've got two geologists on different shifts, and one's convinced it's rhyolite and the other one's convinced it's sandstone, and I don't know what the other one was thinking. It's clearly not, but that's what happens on a site. And a lot of that is because the most junior people on site are typically the people making those logging decisions, and they may not have seen the geology of the region for more than a few swings. Certainly in today's market of getting new staff, high turnover means low consistency of logging and of these practices. I'm sure we'd all want people to stick to the rules, stick to the sheet, but everyone's got a different interpretation. And feeding into these implicit systems is really taking for gospel what's going in. That in the days of manual sectioning, you had to look at every hole, every interval, and had to make a decision. And some of that that checking of the original data was done at the modeling stage, and now we've lost that. It means we need to place more of an emphasis on that data preparation stage prior to modeling. This is something that perhaps we can pursue using machine learning. Can we use machine learning to do some of this data preparation? Can it say, hey, your code SS looks awfully like sandstone. Are you sure you want them as two different units in your model? So there's a lot of scope for where we can head with this, rather than just assuming the same limitations that we had for the past decade of implicit modeling techniques.
Yeah, Richard, just following on that, yes, we've got a prototype which is only very, very fresh, and looking forward to exposing it to customers shortly and getting customer feedback, whereby we can rapidly generate a machine learning model. We've proven that. We've got customers using it in our early access program, and is then to be able to design drill holes, which we've got lots of tools to design drill holes, and feed the machine learning values back into those drill holes, and provide the geologists in the field with a recipe of what they expect in that hole. And as they log the hole, they can see, here's a predictive geology, and then just go through and log their actual geology against that, immediately giving them feedback as to how the modeling is going. If they're working away and it's got basalt, and they're logging basalt and it says basalt and that's all good, and then suddenly they come across some type of dolerite dike, but the machine learning model doesn't have dolerite dike, instantly they can flag, wait on, we need to have a look, our model's not up to, is not up to date, or there's more complexity than we think. So that's something that we're going to be releasing in the not too distant future. It's still in an internal prototype form, but certainly exposing that. I think that's going to add another value, especially where operations have got shorter staff. And I know, being at uni teaching this morning, there's not a lot of students doing the geology sciences anymore, unfortunately. So we're going to have to use some of these smart technologies to help them out, to guide them, to help them process data. So if we go out there and you log on to your shift and you get an email saying this is what you expect out of your holes that you've planned today, they can just go out and log accordingly. And the model is always a model. The actual logging should take precedence, but at least you've got a really good guide of what to expect, maybe when to stop the hole, maybe when to extend the hole, but also to flag, hey, look, I've got to go back and just talk to our resource model or look at it myself. There's something that's come up that's unexpected, and it gives you that feeling that, hey, look, we've got a bit more understanding, a bit more control on where our modeling's at.
Yeah, thanks, Steve. We're moving towards the end of our topics, but we're not going to get away lightly without some participation from the group. So what I'm going to ask now is, we've talked about a lot of topics, things that we're aware of, things that we see as important. I'd like everyone to put one comment in the question and answer box on what they want from all of these things we've talked about. If you could have one thing that we go away and deliver with your maintenance dollars, or as a targeted product, or as a direction for the company? What is something that would really excite you that you could do or would like to be able to deal with from one of the topics that we've discussed? So put something down. If it's something that we haven't talked about, put it on there as well. If things aren't on our radar, we are less likely to be developing them. So put them in now. When we've got a few, we'll run through the comments quickly. If anyone does have anything burning that they'd like to bring to the discussion, let us know as well. But otherwise, me and Steve will be quiet for a minute. We'll let you do your typing. Put in your short wish list of what you'd like from Maptek to make your job of dealing with complex data easier.
Thanks, Richard. I'll take the opportunity to have a drink.
We'll let Colin off because he's already answered one, but everyone else, if you could put something down. If you don't have anything there, we'll take that as you're perfectly happy with dealing with complex data, and we won't have any complaints after the call.
Sorry, Richard, and just a note, we have got Main MCF working in a Maptek workflow, so those that are familiar with that, so as part of the automated process, we can call any Maptek product within that workflow process, workflow editor. We can also call in external Python scripts, where we can call external products that are third party to Maptek and integrate them all into a consistent workflow. Repeatable, visible, you can track where things are at any one stage. So no doubt, if you're not familiar with that, so just get in contact with us and we'll expose you to where you can learn about that. And again, it's all about tracking and keeping a consistent process as people change in your organization, data changes, processes changes. We see that over the generations, lots of people with a script-based process, and that's really good. While the person who wrote all those scripts and still works with you, but as soon as someone leaves, that can get very hard. So the workflow is a very visual way of doing that, and a lot easier to track what's going on, a lot easier to pass off onto someone else. Whether that be your someone that succeeds you in the organisation, or someone that's just your alternate in a FIFO operation.
Yeah, thanks. And thanks, Lara, for the comment. Better integration of all data we currently use. We currently use way too many different software programs between individual geos and different departments, e.g. production, life of mine, and exploration. I think that's two key points there. One is really integrating all the data into our modeling and doing it in one interface rather than using multiple discrete programs for different tasks, having to run through different steps, different users' experience or expectations from them. Really having one modeling system able to take as much of that raw data or process data as possible is something that would make life easier for me. So I'm sure it would make life easier for you all. Another comment from Colin: how easy is it to model lithologies and structural changes across large scale faults? And that's the burning question. When we've got faults, should we be modeling the geology across the faults? And that's something that I've seen in some of your work, Steve, with Domain MCF, how the predicted faults will quite happily truncate data if the model suggests that there is none of that lithology on the other side.
It does a really good job, and I'd love to show a lot of examples, but unfortunately all the data that we've got of complex geology belongs to you, the customers on the call, and we've signed non-disclosure agreements, so we can't disclose any of that. But graphically, I could probably show 50 different examples from 50 different deposits of structures and how they truncate nicely through the machine learning model. And as always, the more data you've got, the better it is. We're talking data sets of 8,500 holes. We've got one in the US and 90,000 holes. The more data you've got, the better it is in terms of the outcome. But structure is, as I said before, one of those surprise outcomes. We didn't build it to manage and model structure, but it's doing a really, really good job. And if someone is quite happy for their data to be shown, happy to do a live demonstration of some of those complex structures and how they've been modelled. But up until we've got some sign off, unfortunately, it's just you and Rich and I just talking about it. That the challenge out there. I know there's a lot of people on this looking at the list who we're already talking to, already using Domain MCF in early access. If you're not happy to do a demonstration of your data to you, it doesn't take much, just a CSV of your data, and that's all I need. Happy to sign non-disclosure as required, and probably one group I had the data. Then with 2 hours we had a session, and that was how quick it was to build a model and show it to them with enough confidence that I was happy to demonstrate it to them. So the data was very clean, just went straight in, got the model straight up. So doesn't always happen like that, as we've talked about. Data preparation is key, but don't be bashful if your data's not 100%. It's Domain MCF is a good tool to do that validation to pick up those things you can improve on.
Excellent. We'll wrap it up now, and thanks for the inputs on that last topic. So non-functional constraints, such as the amount of time we all have to do our jobs, was a nice topic to finish on. And while we could continue this discussion, I'm sure constrained by time, perhaps even we have some complex data that we need to be attending to, so we'll wrap this up. I'd like to thank you all for participating in the discussion, and would like to open up the channels through Steve, myself, or your local Maptek representative to continue discussing the problems you face with modelling complex data and how we can move forward into the next 40 years at Maptek. You'll see there's a short survey popping up on screen, so answer that before you go. And remember that we have, or be aware that we have scheduled a webinar in 3 weeks discussing some of the solutions that we're taking for some of these problems to tackle the issues of data complexity. So if you're interested in this, sign up to see some of the direction ahead and continue this journey into what we develop in the future. So thank you, and we hope to see you all in 3 weeks.
Yeah, thanks, Richard, and I look forward to working with you on that one. I know I've had a preview of what's to come, and it's a really important part of Domain MCF, which is just a processing engine. It is a preparation engine, so looking forward to it.
Thank you.
Thanks, everyone, and bye.